Thank you for coming to my talk, the Mars Wind Project, mapping prevalent surface wind direction on Mars using deep learning. So the project motivation is the following. If you look at Mars, we have actually few measurements of wind direction in the lower atmosphere. Yet, this is a very important and interesting thing to understand because wind direction gives us a clue on Martian weather, but also more broadly on Martian climate. As a geologist, I know that bed forms can preserve currents and ancient wind direction can be preserved as well. So there's a lot of interest here of measuring wind on Mars. And as a matter of fact, it has been attempted before. Here's an abstract presentation by Rubanenko et al. In 2011, where what they did is they used a direct deep learning approach to reconstructing wind direction on Mars. This is interesting work and this is good work. However, there might be some limitation to this approach. The first thing is it's extremely time consuming because you have to manually identify each one of the dunes. The second thing is that this actually comes down to manual feature extraction because you have to manually find the Bajan dune and manually extract the wind directions from them. And these two things combined means that you end up with a very limited data set. In the paper, they talk about 1008 images and a total of 5000 dunes being identified in these 1000 images. And we know that small data sets are a problem with deep learning. And we know this because we've done a lot of research on this. And I would encourage you to look at the poster of my PhD student, Harriet Dawson. The point is that we show that with different image sizes or data set sizes, so 7,000, 41,000, and 104,000 images, we end up with very different fitting, and small data set always overfit. So we need a lot of images even when we use transfer learning. So what we'd like to try is an alternative, a proposed alternative approach. So we know that on Earth we have a lot of good satellite images, but we also have a lot of good ground data or ground truthing data on Earth. So we can essentially create a solid data set on Earth. We can train on Earth and apply that model to other planets. And wind, of course, can be reconstructed by dunes. So this is an example of the Rub al Khali in Saudi Arabia. You can see a beautiful satellite images of Earth's dune. And if you compare this with Martian dunes these are spectacular dunes from the Martian North Pole, you can see that their geometry and the fundamental principle that leads to the formation of dune is the same. Right, so let's look a little bit at our approach. So the first step is we need to build a data set. So data acquisition is important. And for this, we need two things. We need satellite images, satellite data, and we need wind data as our label. So for satellite, we can use Google Earth Engine API or GEE. And specifically, we ended up using the Sentinel-2 dataset because it comes at 10-meter resolution. So it has a very good resolution for Earth satellites. So an image that we acquire looks something like this. This is a typical square we would acquire. It's 0.1 degree of latitude, which amounts to about 11.1 kilometer in terms of spatial dimension. The API that we use for the wind direction is the ERA5 dataset. We use the average monthly data that we average over 10 years. And we selected both images, satellite images, and wind data from 5 Earth deserts. And in those deserts, we had region with sand and dunes, and we had region with only rocks and mountains. So each one of the images need to be labeled with the wind data. So the first label, of course, is the position of the image, but we also have the wind direction, which is the primary data we're trying to reconstruct. A traditional way to do this is to use the sine and the cosine of the angle to encode the wind direction. And then we also encoded, for completeness sake, the strengths of the wind in meter per second. But of course, this is very, very large and there are many dunes on this surface. And for deep learning, like I said, we want to have more images to be able to get better training. So what we do is we take this large image and we split it into smaller images of 2.75 by 2.75 kilometers. And these are the images that we will use for the training. We use the same wind direction and wind strength for each one of these images. The images are then separated into 2 categories and 6 folders. Either we see dunes and we visually inspect each one of these images, or we do not see dunes. So we have a binary classification here, dunes or no dunes. Each one of these category has 3 folders. We have a train set of about 30,542 images. We have a validation set of about 3,948 images. And we have a test set of 8,413 images. Let's talk a little bit about the test set. Because we're dealing with geographical data, it's important to train our algorithm so that it generalizes well. And for this, we use the train test geographic split. We take 80% of the data set geographically located in one part of the image, and that is going to be our training and our validation set. That 20% of the image is kept separate, and that's our test set. And all the result I will show you is on the test set that is geographically completely separate from the validation and training set. And if we look at the training set, we can actually increase the size of the training set. The data augmentation that we have applied here, because we need to keep the geometry of the dunes the same and we need to be mindful of the direction of the wind, is relatively simple. So for one image, we can first apply one symmetry, and each one of these images can also be applied 4 rotation, or 3 rotation plus the original image, which means that for each original image we obtain 8 training images. So that means that our training set, but the one we'll use to train our algorithm, has 244,336 dunes and the same number of images that don't have dunes. So it's completely balanced, and it's nearly 500,000 images large. Right, so once we have the data set, we can start training our algorithm. And the first algorithm we'll train is an image classifier. Of course, some of the images are not going to be of high quality, so we had to first manually clean our data set to remove any problematic satellite images, and this was done manually to ensure data quality. We will train 2 algorithms, one image classifier, but also one wind regression model. The particular model that we will use is a CNN, a convolutional neural network, and we settle on using exception. And I'm showing you here the results of a paper published this year to detect COVID using CNN, so with X-ray of lungs. And they have also used exception like we did. And exception is a good model in part because, unlike conventional CNNs, it applies depth-wise convolution before applying point-wise convolution, whereas most others just do point-wise convolution. But really for us, the choice of exception was a pragmatic one. We tested multiple architecture. Exception is relatively small, so it has less trainable parameters, which makes it appropriate for a relatively small data set. We think that 500,000 image is actually not that large, believe it or not. So once we have done our model, we can test them with the validation test, and we can improve the models until we get to a model that gives us the best accuracy, precision, and results. So let's look at some of our results. So first, let's look at the results of the classifier, and I'm showing you here a confusion matrix, and you can see on the diagonal the class that were correctly classified. You can see that we did a pretty good job at actually classifying about 95% of the images. We have about 5% error and an accuracy of about 95.4%. So a pretty good accuracy. What we're really interested in is actually the precision at which this classifier works. This is a precision recall curve. There is a trade-off between precision and recall, and what we want is we want to favor precision in our case because we can live with missing a few dunes if we're more confident that the images that we have truly contain dune and we can get a good wind direction from them. So if we put the threshold, the decision threshold at 50%, which is typically the default values, we obtain a precision of 80.84, so 84%, and a great recall of 99%, but that's not really what we want. So we can move that threshold. And if we put the threshold very high at 97%, then we get to a precision of 97% and a recall of 91%. That means that we will get about 91% of the dunes correctly recognized in the data set. That means that about 9% of the dunes will classify as not dunes, so we'll lose those. We won't be able to use those for for identifying and regressing wind direction. But the good news is, of the images that the classifier tells us are dune, 97 out of 100 will truly be a dune, so we'll have only a 3% error rate of trying to predict the wind direction on something that is not a dune. So that's actually a satisfying classifier for our purpose. So now we can look at the wind regressor, and the best way is to show you this image of the test set, of a few completely randomly selected images from the test set. In red, you have the actual wind direction as per label, and in blue, you have the predicted wind direction. What we find is that we have a root mean square error of 23 degrees. Now, 23 degrees is not too bad, because at least it gives us, a pretty good idea of the direction of the wind. But I actually think it's even better than that, because if you zoom in and look a little bit at the detail of what's happening, most of these blue and red arrows are extremely similar. However, when the model gets it wrong, it gets it really wrong. Here we have a 45-degree error, which is almost the maximum error you could imagine between these two wind directions. So that root mean square error of 23.06 is really driven mainly by a few large errors that we have, which also means that if you predict a lot of wind direction in a region and you only look at the most common direction, you will probably get the correct regional wind direction. So that's very, very encouraging for applications. And speaking of application, the whole point of this talk is to apply it to Mars. So let's look at how we can do this. So to predict wind on Mars using our classifier and our regressor, we will use data coming from the Murray lab, and specifically it's the CTX imager from the Mars orbiter, and that has a resolution of 5 meters. Okay, so we'll have to drop the resolution of these images to be similar to the Sentinel image resolution of 10 meter per pixel. And we use the global CTX mosaic that is provided by the Murray lab. And the good news is we can actually cover the entire red planet. So let's look at an example here. Each one of these images is actually fairly large. It represents about 118 square kilometer. And keep in mind that what we're predicting is a 2.75 by 2.75 kilometer square. So in this one image, we're going to now make about 560 predictions, individual predictions on small squares, to determine whether or not there is a dune, and if there is, what the wind direction is. And what's going to happen in the next image is you will see arrows. Where there are arrows, a dune was predicted to be present, or a dune field, and a wind direction is taken from this. And when there is no arrows, it means that there is no dune being detected in this particular location. And now you can see we have a lot of these arrows. And what's really interesting is most of the arrows point in one mean direction, which gives us the mean wind direction. And that's how we can, using Earth data, apply the same approach to Martian satellite images and predict wind direction on Mars. So that brings me now to my conclusions. So in conclusions, using Earth's sandy deserts yield good predictions of wind direction. It definitely works on Earth. Our first applications to Mars, and I must say these are the early results, yield realistic wind directions. But we do need to test our algorithm a bit more on Mars, because we are, of course, making assumptions that what we train on one type of satellite on Earth, Sentinel-2, is also usable on the Mars CTX orbiter. And so that means that we need some label data to make sure that we are actually predicting the right thing. So stay tuned. This is still work in progress. But I do think that planetary transfer learning is a potential quick way to apply deep learning to our solar system because we have a lot of labeled data on Earth. And if it works on Mars, then there's no reason why we cannot use our algorithm on Venus or other planets. Thank you very much for your attention, and I'll take any questions.